Hi, welcome to chapter 16, chemistry of benzene, electrophilic aromatic substitution. My name is Ramon Rios and I will deliver this lecture. Okay, remember that this is a recorded lecture that is in any case a substitution of for the presence in live lectures. Okay, this is only to help your study and a place where you can recover all what we said in the lecture room. Okay, we will talk about the chemistry of benzene. Okay, and concretely we will talk about electrophilic aromatic substitution reactions, the bromination. We will talk about other aromatic substitutions like could be chlorination, nitration, and finally we will talk about the alkylation and anilation of aromatic rings that is called the Friedel-Crafts reaction. Okay, important concepts is the aromaticity. Okay, remember that we talked about it in chapter 15. Is the stability associated with benzene and related compounds that contain a cyclic conjugated system with 4n plus 2 electrons in the p system. Okay, we will talk about the electrophilic aromatic substitution, and this is basically that an electrophile reacts with an aromatic ring and substitutes one of the hydrogens for the electrophile. Here you can have the reaction. Here you can have the reaction, okay, where the benzene ring reacts with the electrophile, substituting one of the hydrogens for the electrophile. Okay, electrophile can be a halogen, can be a nitro group, a sulfonic group, a hydroxyl group, an alkyl group, or an acyl group. There are several options. Okay, and you see here all the possible products. How is working? Well, the reaction, as you can imagine, is slightly similar to the electrophilic alkene addition. Okay, remember that in the alkene addition, what we did is a double bond is that pair of electrons of the p system of the double bond is attacking an electrophile. In this case, for example, hydrogen chloride. We are forming the carbon-hydrogen bond, and we are forming a carbocation. Then the carbocation is reacting with the nucleophile, the chloride, forming the addition of the product. Of course, we are talking a compound that despite aromatic ring has 3 double bonds, his chemistry is very different to a chemistry of the double bond. Okay, the first main difference is that are more unreactive than not double bonds. Okay, remember that when we have a double bond, this is reacting with bromine very easily, forming the bromonium ion, etc., etc. Okay, remember, a double bond is reacting with brom to form the bromonium ion. Okay? However, when we have electrophilic aromatic substitution, we have electrophilic aromatic substitution over a benzene ring, what is happening is that the bromine, for example, is not reactive enough. We need to add a catalyst, and the catalyst that we use normally is iron tribromide. Okay, where is reacting with bromine, as you can see here, forming bromide positive, okay, plus iron tetrabromide negative. The bromide cation plus the iron tetrabromide anion. Okay, this brom positive, this brom cation, basically is reacting with the benzene. A double bond of the benzene is attacking this brom positive, forming a very similar intermediate than the carbocation that we obtain with the double bond, as you can see here. In this case, as you can see, we can stabilize this carbocation by resonance with the other double bonds of the aromatic ring. Okay? That means the intermediate is exactly the same than in the electrophilic alkene additions. For double bonds or aromatic rings, the first step is very similar. The only difference is that we need to activate the electrophile that normally works very well with alkenes. In the case of aromatics, we have to activate using a catalyst. In the case of bromine, iron tribromide. Okay? But as you can see here with the energy diagram, is very, very similar the energy diagram of both. Both, we start the reaction, the pair of electrons attacks the electrophile, we have a transition state, and then we arrive to the intermediate, where the intermediate is the carbocation. Okay? When we have the carbocation, here is how is different the addition to double bonds and the addition to aromatic rings. Basically, in aromatic rings, the best continuation or the simple continuation is regaining the aromaticity. In order to regain the aromaticity, as you can see here, what we do is we eliminate this hydrogen here. We do an elimination of this hydrogen. The pair of electrons of the hydrogen are going, that are forming the carbon-hydrogen bond, are forming the double bond. We lose a proton, and what we get is the aromatic compound again. We get the aromatic compound again, the aromaticity, but substituting the hydrogen by a bromide, as you can see here. Okay? Remember that in the case of an alkene, what we have is that the nucleophile is added to the carbocation. Okay? Why this difference? Basically, because, as you remember from lesson 15, aromatic compounds are very, very stable. If they are very, very stable, this will be the great benefit of the reaction. We gain stability, that means the system will want to gain this stability, that means that it's more favorable to get the elimination and regenerate the aromaticity than not to add a nucleophile in the carbocation, because if we add a nucleophile in the carbocation, we will have a compound that is not aromatic. Ergo, will be less stable. Okay? Here you can see the energy diagram. Okay? Again, we start with the benzene plus the bromine that we need to activate. What is happening is that the pair of electrons attacks the activated bromine. We are forming the transition state, and then we go to the intermediate that will be the carbocation. Once we have the carbocation, what is happening? We eliminate the hydrogen, okay? And we regenerate the aromaticity again. We regenerate the aromaticity and we get the final compound. Check that here I draw what will happen if we have a nucleophile addition in the carbocation. And as you can see, this compound here will be by far more unstable than not the aromatic ring. This is the reason why this reaction is going to the final products. Okay? For example, we can do the problem 16.1. Monobromination of toluene give a mixture of 3 bromotoluene products. Grow and name them. Okay? We can grow it basically. Basically, this is toluene, okay, and we have to do the bromination, and they say that we have 3 products. A priori, without knowing anything about the regioselectivity, what we can have is the bromine in the ortho position. Remember, the ortho position is the 2 position, meta position, or para position, where meta is the 3rd position, is the 1 free position, and para is the 1 4 position. And if we have to name it, the first one will be a 2 bromotoluene or orthobromotoluene, the second will be free bromotoluene or metabromotoluene, and the last one will be 4-bromotoluene or para-bromotoluene. Okay, you can use the name that you prefer. Okay, next we can check the reaction about the aromatic chlorination. It's exactly the same than Bruce bromine. Okay, the only that we need to consider is that the chloride is less reactive than the bromine, but basically when we are using a catalyst, in this case iron trichloride, what we will get is the same reactivity. We will add the chloride instead of a hydrogen, and you can see that I add an example of real life for the synthesis of loratadine, okay, where they did a chlorination of this aromatic ring using chlorine and iron trichloride. Okay, the mechanism will be exactly the same that we did before. Will be first the double bond of the aromatic ring is attacking the chloride, the activated chlorine by iron trichloride. We form the carbocation that is an intermediate, a minimum of energy. Remember, in the energy diagram, the carbocation will be a minimum of energy, and then we eliminate the proton that is in the same carbon that we add the chlorine to regenerate the aromaticity because it's more stable, the final product. Okay, we can do exactly, or not exactly, but a very similar reaction with the nicration. Okay, how is working the nicration? Basically, we start with a mixture of nitric acid and sulfuric acid. Here you can see nitric acid. Okay. And then what is happening is that the sulfuric acid is able to protonate the nitric acid, as you can see here. We transform this OH, this hydroxyl group, in a water group that is a very good leaving group. Remember, when we want to eliminate alcohols in organic chemistry, we add acid in order to make water as a leaving group, because hydroxyl groups are very bad leaving groups, water groups are very good. Then once we form the water, basically we eliminate water and we generate this compound, this nicronium ion, okay, this NO2 cation, okay, and then the reaction is exactly the same. The benzene, a pair of electrons of the benzene, of the p system of the benzene, is attacking the nicronium ion, and once we have the first addition, we form the carbocation intermediate, hydrogen is removed, proton is removed, and we get again the aromaticity obtaining nitrobenzene. Okay, we can do a similar problem with that we did before. Basically now is how many products might be formed on chlorination of orthochylene. Remember, chylene is dimethylbenzene. Okay, well, if we have orthochylene is this. Okay, we can have the chloride. In position 3 or in position 4. Okay? If we put the chlorine in position 1, 2, 3, 4, 5, we will get the same, no, in position 5 also, sorry, we will get exactly the same that if we have in position 4. Okay? If we have the meta-chylene, okay, the meta-chylene, what we have, we can have the chloride in this position, in the middle of the two methyls. Okay? We can have the chlorine in this position, in position 4, or we can have the chlorine in position 5. We have these three possibilities. If finally we use the para-chylene, okay, where the two methyls are in 1,4 disposition, what we get is that the only product that we can get is this, because all the other products are exactly the same. Okay? That means we can get 6 products if we add chlorine, or we are doing the chlorination in a mixture of Chilenes, orthometapara. Okay, then we can talk about alkylation and acylation of aromatic rings. Basically, we will talk about the Friedel-Crafts reaction. Okay, the Friedel-Crafts reaction was discovered by Friedel and Crafts long time ago. If you want to know about more about the Friedel-Crafts reaction, basically I recommend that go to Name It Reactions. That is a web page where you can know everything about every reaction that has a name. Okay? But basically in this reaction is the addition of benzene to a chloroalkane, alkyl chloride. Okay? What is the first step? Well, again, alkyl chlorides are not enough electrophiles to react with benzene. That means that first we need to activate the alkyl chloride. In order to do this, we need aluminum trichloride. When we do aluminum trichloride, we add to the alkyl chloride. What we do is that the aluminum trichloride takes the chloride from the alkyl chloride, generating a carbocation in the alkyl group. Okay? Of course, for a more advanced courses, this carbocation can rearrange to obtain a more stable carbocation, but this is not part of this course. Okay, once we have the carbocation, this carbocation can react with the benzene ring in the same way that we react the bromonium ion or the bromonium compound before, or the nichronium compound before. Okay, basically the pair of electrons of the p system of the aromatic ring attacks the carbocation, as you can see here, and then we form the carbocation intermediate. We lost one hydrogen, we remove one hydrogen to regain the aromaticity, and what we have is the alkylation of a benzene ring. Okay, what is the limitations? Well, the limitations is one that we said, is that the carbocations sometimes can produce rearrangements. That means that we move the carbocation in order to get a more stable carbocation. Okay, this is the mechanism. You don't need to know. It's only a culture. Okay, and the only limitation is that the final product is basically more active than the starting material. Here is the starting material, here is the final product, and this final product is more active because this group, the alkyl group that we add, acts as a donor. Okay, remember that stabilize carbocations by hyperconjugation, and that provokes that the final compound is more reactive than the starting material. Means that we can do polyalkylations very easily. Okay, and this is a side reaction that we don't want. If you want a reaction that is working very well, that means the alkylation of Friedel-Crafts, we don't use it because basically it's very difficult to control. Only in very special occasions you can control a Friedel-Crafts alkylation. But on the opposite side, the Friedel-Crafts acylation is working very, very well. Okay? Basically, the Friedel-Crafts acylation, the main difference is that instead to use a alkyl chloride, now what we use is a acyl chloride. Okay, we are using this compound now, acyl chloride. Okay, and the mechanism is the same. First, this is reacting with aluminum trichloride, as you can see here, the acyl chloride. We need to activate the acyl chloride, and what we generate is this acyl cation. Okay, we generate this acyl cation that, as you can see, is stabilized by resonance. Okay, and aluminum tetrachloride anion. Okay, then our benzene ring is reacting with the acyl cation. Okay, the pair of electrons of the aromatic ring of the p system attacks the carbocation of the acyl cation. Okay, forming the carbocation intermediate that we saw before, and then again we eliminate a proton to regenerate the aromaticity to get the final compound. This reaction is working very, very good, first of all because we don't have carbocation rearrangement in acyl compounds. Why? Because the acyl cation is stabilized by resonance. Second, the final product is less reactive than the starting material. That means that we also avoid the possibility to have polyacylations. Okay? Problem 16.5. Which of the following alkyl halides would you expect to undergo Friedel-Crafts reaction with rearrangement, and which result? Okay. If we take the A, ethyl chloride, we cannot have any rearrangement because basically whatever move the carbocation, we will get the same carbocation. In the second one, we have a secondary carbocation. That means it's possible that we can stabilize by the migration of one of the methyl groups, could be getting the final product more stable. The third one is clear. This is a primary carbocation when we remove the chloride, and this will be rearranged to form a secondary carbocation that is by far more stable. The third one will form a primary carbocation that also will do a rearrangement to get a more stable carbocation. And finally, chlorocyclohexane. When we form a chlorocyclohexane, what we get is a secondary carbocation that we cannot rearrange because everything that we can get will be exactly the same to form the final product. That means A and E will not rearrange, while all the others will rearrange. And that's all for today. Okay, remember you have the study questions for problem solving sessions from the textbook, chapter 16, questions 1, 3, 5, 7, 36, 50, and 54. All the answers are in Blackboard. I put it, all the answers, make my hand in Blackboard. And please read the textbook, okay? Chapter 16, 1 to 3. Thank you very much. And see you next day.